Here in exercise 5, we are going to explore the concept that matrix addition and matrix scalar multiplication are commutative and distributive. And what do those two properties mean? So here is an equation that tells us what this means. So imagine A and B are matrices. Sigma is a scalar, so just one number. So here we say that sigma times the sum of A and B equals sigma A plus sigma B, and that equals A times sigma plus B times sigma. Again, if you are new to linear algebra and you're just coming across these terms, this may seem painfully obvious. Like you learned this when you were, I don't know, 7 years old or something. Why do we have to learn this again in an advanced level linear algebra textbook? It turns out that this is not trivial the way that it is for numbers. So if sigma and A and B were just individual numbers, these were all scalars, like sigma is 2 and A is 3 and B is 7, then this is trivial. You have known this for your whole life. But in linear algebra, this is really not trivial. And you will see when we get to vectors and matrices and multiplications that these properties do not necessarily hold. And sometimes these properties do hold for certain special matrices, but not for other matrices. It gets pretty weird. So we have to go through this stuff methodically. Okay, anyway, so sometimes it's useful to prove things mathematically, but in other situations, which is the goal of this exercise, it also helps you build intuition for concepts in linear algebra to demonstrate it through coding. Okay, so what you want to do here is generate two matrices of random numbers, both matrices of size 3 by 4, and we're adding these together. So you know that these matrices need to have the same size. Okay, and then we also generate a random scalar. Again, a scalar is just a number. It's not a vector. It's not a matrix. It's just one lonely number all by itself. Okay, then implement the three expressions in the equation. So that's this. There's this expression, and then this expression, and this expression. And we need to figure out a way to confirm that these equalities really hold. So here I have my two random numbers matrices, and I have a random scalar, which I'm calling S for sigma. Okay, so then we have the three expressions. So this is sigma times the sum in parentheses, A plus B. And then we have sigma times A plus sigma times B. And then here, expression 3 is A times sigma and then B times sigma. So if the commutativity and distributive properties hold for matrix addition and scalar multiplication, then all three of these expressions should be exactly equal to each other. Again, this is not trivial because you'll see that when we get to vectors and multiplications, that these different expressions, first of all, some of them might be valid and some of them just might be invalid. And also, even when they are valid, they might give different results. Okay, so there's a couple of different ways that you can show that these are all equal to each other. If they are equal, so if this is true, x equals y equals z, then 2x minus y minus z equals 0. This is just one of many ways that you can show that these three expressions are equal to each other, and this is the way that I'm illustrating here. So 2 times expression 1 minus expression 2 minus expression 3. If these are all equal to each other, then the result should be just lots and lots of zeros. And we get lots and lots of zeros. So this is not a proof. This is an empirical demonstration, which will help you improve your math, linear algebra coding skills, and also help you develop intuition for these kinds of operations.